Excellent. So I don't think we need any introductions. We know each other from last time. And I will not delay this, and I'm going to ask Victoria to go and present us their work on overheating.
Thank you. I'll share my screen, but not completely because I want to still be able to see you all, because I'm working on a laptop. Believe it or not, I'm not in the office at 10 p.m. I'm just in my spare bedroom. Wonderful.
Yeah.
So it's just loading. Great. Can you all see that?
Yes.
Cool.
Yes.
All right. I'll make a start. So yes, hello. I'm Victoria Threadwell. I'm a senior building scientist at the Ministry of Business, Innovation and Employment in New Zealand. I'm in a team called the Building Performance and Engineering team. So basically, we're the technical team behind the New Zealand Building Code. And I have Richard London online as well, who's my line manager. So today I'm going to speak to you all about a project I'm leading on our overheating assessment methodology that we've developed for New Zealand. And I'll also cover some New Zealand context, the 3 parts of our overheating assessment methodology, and also potential areas for collaboration with you all. So in New Zealand, although we're a really a similar land size to the UK, Italy, and Japan, we only have 5 million people. This has given us the luxury of space, with historically many New Zealanders living in standalone homes, even in central cities. However, over the last decade, things have changed rapidly. In 2012, townhouses were around 5% of our building consents, whereas now in 2026, almost half of our building consents are townhouses. This is due to urban planning rule changes, as well as to address issues with the cost to land, but also to encourage more vibrant urban centres. This image here, it's generated by Copilot, but it kind of shows on the side here the standalone houses that we used to live in quite commonly in New Zealand. So Victorian villas around the early 1900s. These standalone homes were quite common in the 1950s, 60s and 70s. But now within our main city centres, townhouses and apartments are the most common, with some urban, kind of outer urban areas having still standalone homes, which are quite big and not really designed to address issues with overheating, but I'll get to that soon. So the changes in our housing types, homes becoming more airtight, and also changes to the climate have meant that overheating has become a widely reported issue in New Zealand, with it making headlines most summers. Some of the headlines are on my screen now. In New Zealand, we have 6 main climate zones in our building regulations for energy efficiency, including subtropical climate in the north, temperate and alpine climates. Although our summers are quite mild, with temperatures typically between 15 to 25 degrees in most regions, where some regions can get above 30 degrees, sometimes during summer. Our New Zealand building regulations have purposes like people who use buildings can do so safely and without endangering their health, and buildings have attributes that contribute appropriately to the health, physical independence and well-being of people who use them. However, although we have requirements around underheating in early childhood education centres and retirement homes, we don't currently cover overheating in our building regulations. So in response to overheating being reported, like the news articles I showed previously, over the last year, we've developed a draft overheating assessment methodology for New Zealand, which is now a complete draft methodology. This overheating assessment methodology was developed with a range of technical experts in overheating from across New Zealand and Australia, including Emeritus Professor Richard Adair, who you may have heard of, Dr. Masan Sagari, who presented in our last meeting, as well as people from New Zealand, such as our Building Research Association New Zealand, our community housing provider, Kāinga Ora, and the Ministry of Education, who have all done extensive modelling or monitoring of overheating in New Zealand. Our draft overheating assessment methodology has three main parts: a simulation methodology, which is currently based on CIBSE TM59. This outlines the modelling assumptions such as occupancy schedules and loads and inputs to use. A calculation, we've decided on the SET star or standard effective temperature calculation, which combines air temperature, mean radiant temperature, relative humidity, and ventilation rates with the personal inputs of metabolic rate and clothing level. And then a pass-fail criteria, which is based on hours. So in other words, how many degrees a space is above a certain temperature threshold, as well as for how long. Where we vary from other countries or other methodologies is humidity is key in New Zealand, which is why we're using the SET star formula. This is due to the northern regions of New Zealand being subtropical. There have been studies in Australia and New Zealand which have used CIBSE TM59, and it's shown that it's been too stringent for some of our regions. This is in comparison to methodologies that use operative or resultant temperature, which is based purely on air temperature and mean radiant temperature. Our focus is also on health and well-being rather than comfort. This means we're concerned with limiting heat stress and heat strain of occupants rather than general comfort of a home. Although our overheating assessment methodology is complete, we are now refining the methodology through applying it to a range of residential archetypes. We have 16 residential archetypes which reflect contemporary architecture in New Zealand that have been developed as part of a separate project. These include townhouses, apartments, and standalone houses. Some of them are shown on my screen now. These will be used for modelling across upcoming building code updates. So solutions are coordinated across the building code for overheating, ventilation, internal moisture, and energy efficiency. We have formed a technical panel, again, to assist with our overheating analysis, as well as engaging engineering consultants to complete thermal modelling for us. This piece of work will apply our draft overheating assessment methodology using IES and Energy Plus to these residential archetypes that are on my screen. From the results from applying the overheating assessment methodology, we'll be able to answer questions such as what should the pass-fail criteria be, or which weather file to use. For example, the design summer year 1, 2, or 3, or maybe something else. This methodology will be published on our building performance website later this year. However, as regulation changes are needed to include overheating, this will be voluntary for people to use rather than a requirement for a building consent. After the overheating assessment methodology is published on our website for voluntary use, we will shift to updating regulations to include performance requirements around overheating. We'll then develop the compliance pathways for assessing buildings for overheating. There will likely be two compliance pathways: the overheating assessment methodology that I presented today as a detailed or more complex compliance pathway, and also a simple rule of thumb compliance pathway, which may include things like limiting glazing size, night purge ventilation, or external solar shading. Collaboration is key in solving some of these complex issues. So we're in regular contact with universities and research organisations working on overheating throughout New Zealand and Australia. We're lucky in New Zealand as an overheating roundtable has been created, which includes people working on the impacts of heat waves on people from an outdoor urban comfort perspective, health perspective, and also building perspective. So this is made up of mostly universities across New Zealand. This means we have an existing forum to discuss our thinking with, as well as to coordinate research with to answer any research questions we have. On my screen now are some of the research questions that we'll be answering through our current piece of overheating work. And if you have any feedback or thoughts on these questions, please feel free to reach out if you'd like to discuss these in more detail with us. So these cover defining a heatwave for the built environment. I understand Annex 80 has done some work on this already. Weather file selection for assessments, as this will have the largest impact on the pass-fail rate of an overheating assessment, so it needs to be carefully chosen. And it was interesting in our last meeting to see that France has chosen a more stringent weather file to use, whereas our current thinking is to use a less stringent weather file, but maybe through this forum we'll learn more about that. And also another thing that we're developing is the modelling assumptions based on, so this will be like load profiles and energy loads to use in buildings. At the moment, our existing methodology is based on probably out-of-date data for New Zealand, but actually the brands or our Building Research Association New Zealand has got updated data that will be feeding into our piece of work. And also we'll be looking at how to define heat stress and heat strain thresholds. Cool, thank you. Please reach out if you have any questions or would like to discuss any of this further. Thank you.
Thank you for this very interesting presentation, Victoria. If you could put back your last slide.
This one? This one.
So just for information, can you discuss any work that you have done with respect to these questions, or what you have learned to date?
So what our current thinking is around these 3 points is the definition of a heat wave. Without defining that will determine, we can't determine which weather file to use. So that's kind of where our current thinking is. Obviously, we have the design summer year 1, 2, and 3 weather files, which hopefully most of you are familiar with. But they don't necessarily contain the most extreme heat waves. So from a regulatory perspective, we're trying to understand whether we should be getting people to stress test their buildings against the most extreme weather conditions, like what you're doing in France, or whether we should take a more conservative approach and just, for example, use a design summer year 1 weather file, which is kind of an averagely warm summer that would occur every 7 years. So yeah, that's my thoughts on the first point.
Okay, thank you. Before going to you, Roberto, is this something that France, for example, uses to define a heat wave, Louis?
Yes, we are for the climate field or for
for the climate.
We use the real weather of our 2003 year.
Mm-hmm.
So I don't know the definition of the heat wave for us. It seems to be 15 days of hot weather in our field.
Thank you.
So it's
the duration,
yes,
and
a little bit extreme.
Yeah.
Yes.
Yeah. Thanks. Roberto? Yeah, sorry. Go ahead, Victoria.
I was just going to say, because when you presented last time, Louis, your colleague mentioned that you're using a reference building modeling approach. Was that for new buildings and existing buildings, or just for existing buildings?
The reference, it was for existing buildings.
Existing building. Okay, so for new
Yes.
buildings, you're actually stress testing them against this 15 days of heat wave weather file from 2003.
Yes, we are modeling this for the real situation.
Yeah, right. That's really interesting, because if we did that in New Zealand, we'd be probably concerned that all the houses would fail effectively. Yeah. But
yes, but we define the threshold with this field, so we choose to yes, a threshold that is we are able to succeed.
Thank you. It's all good for us, like things for us to consider and learn from what you've done.
Excellent. Thank you. Roberto?
Thank you, Victoria. You are using SET index. I wonder how you deal with air velocity.
Air velocity?
Yeah.
Well, we'll learn more about how we'll be dealing with it. At the moment, there's the air movement assumption of 0.1 meters per second with no fans. And then there's the assumption of 0.8 meters per second with ceiling fans. They come from SIBC TM59. And then we've got the windows opening when the temperature is above 22 degrees, which is also from SIBC TM59, except for the thing that's different in New Zealand than the UK is our temperatures in some regions get hot. So on a 30-degree day in parts of New Zealand, you would not be keeping your windows open. So at the moment, we're working out how the SIBC TM59 approach would need to be adapted for New Zealand. So, for example, do we have a requirement when you're doing the modelling that as long as the outdoor temperature is lower than the indoor temperature, your windows are open? If you have a security stay, for example, because the city I live in, it gets to 35 degrees sometimes, and it was a very strong warm wind on those days, and you would not open your windows because it would make it far warmer inside than if you had them closed. So yeah. But we're learning more about air velocity and using the SIBC TM59 framework, but adapting it for New Zealand. Yeah.
And regarding the degree hour, it will be on SET also.
Yes, we'll have 3 thresholds. So we'll have a comfort threshold. We're actually using data from Australia. They've done lots of monitoring. So what Masan spoke about in our last meeting, they got universities from throughout Australia to conduct the same way of monitoring, like survey results and monitoring of indoor environment. And from all that data, Richard Adair is developing an adaptive thermal comfort index for New Zealand, which will include the comfort threshold, which is where 80% of occupants feel comfortable within that threshold. And then we'll also be developing the heat stress and heat strain thresholds on top of that. But this is all part of this current piece of work that we're doing, which actually only just started last month. So we're right at the very beginning of it, but we'll learn lots more over the next 6 months or so. Yeah.
Thank you very much.
Mike, sorry.
Thank you. So you mentioned ceiling fans just now. I was just wondering, outside of the glazing size, insulation, are you considering active cooling measures as part of the compliance pathway? That if people say that they have active cooling for a space, or will that be an acceptable pathway, or will it only be done through passive measures?
This is something like once this current project's developing, we're refining this overheating assessment methodology, and the next project, which will probably be this time next year, we start that. We'll develop the actual compliance pathways themselves. But our current thinking on that, which we haven't got to it yet, but we're kind of just starting to think about the next phase of work as well and planning it, is a number of our district plans require mechanical heating and cooling and ventilation in apartment buildings and townhouses in urban areas. So we're thinking that if you by default have to have a mechanical heating or cooling or ventilation system, that there will be another compliance pathway for the overheating assessment. Because obviously, ideally, would have everyone complying using passive means, but that's not realistic. If your district plan is saying you can't have openable windows, for example, then we'll be thinking about how that all fits together. But it's complex because we have so many different district plans for different districts within the country. They all deal with these things in a different way. So we're trying to learn more about how different regions have requirements that interface with overheating as well. And how to bring it all together into one kind of cohesive solution from a building regulatory perspective.
Richard, you've got more to add?
I've got a comment, so if you've got questions, keep your questions coming.
So I did have another question. And it was about the I guess your elemental, your simplified method and your versus your verification method, and it may be too early to tell, but I'd be really interested to see how close or you think that you'd be able to approximate between the two, to have I guess a quality of outcome or equity of outcome from those two different pathways.
Yeah, that's a really interesting question. And yeah, when we get to this piece of the next phase of work, it would be good to I can check back in and see, present where we got to with kind of the final compliance pathways. We've also got a change of government this year, so who knows what's going to happen. Or we may have a change of government. We've got an election, I should say, coming up. So yeah, who knows where we'll end up. But yeah, this is what we're planning for at least. Overheating's been in the media a lot, and so it's definitely front of mind, especially in summertime. Maybe not so much in midwinter, but yeah, it will come around again.
Great, thank you.
Excellent.
Just some additional context there. Predominantly New Zealand's strategy, or at least regulatory requirements, have been based around a heating model, in the sense of we're saying, look, we need to heat. And so certainly through the 1970s, and Mike, who's now joined us, might be able to quote on this, with the energy crisis that happened through there, a real push towards putting insulation into homes. There was one of the first requirements in 1978. And since then, there's been sort of incremental increases. What we're finding, as Victoria's been saying, is that as we increase air tightness, as we increase insulation, we're starting to get cumulative effects of other things like, cumulative humidity and moisture accumulation within buildings, which comes to your comment there, Roberta, regarding ventilation and air movement, because part of that is around evaporation for the purpose of comfort and respiratory rates by which people can become thermally conditioned, as opposed to then getting to the point where maybe we need to go to something which is, shall we say, deliberately cooling air, such as heat pumps, which has become very popular in New Zealand. There are certainly people designing with heat exchange units, which is also some of the passive house movement is pushing that, but they're not very common unless you are in something like an apartment block, where it becomes economically a bit more efficient. At the moment, the weather files have not been looking at something like an RCP 8.5. It's looking at historic weather data at the moment. So this is where the discussion as to whether or not we should be using, should we say, an actual heat wave type event, as is happening in France, or whether we are looking at maybe a forecasted weather file, which is saying that this is what the conditions are likely to be in the future. That's up for discussion and for exploration. But again, we are learning a lot from these discussions here and other discussions that we're having through the IRCC as well.
Thank you, Richard. I see that we are joined by 3 colleagues. So we are going to do our introductions again. So maybe Rajan, can you go first?
Hi, this is Rajan. I am a part of the SEPCH University, which is based out of Ahmedabad, India. And my work spans between buildings, comfort, urban heat, and cooling. Nice. Thank you.
Thank you. It's in Japanese writing, so can the colleague from Japan introduce themselves?
Yagi-san, please. Yagi-san.
We'll go.
Yeah. Yeah.
That's okay. Michael.
Yes, can you hear me? Thank you. You can. Sorry, I asked that because if I turned the camera on, you'd see out the roof of the car. I'm driving home, having volunteered as an usher at a Wellington Film Society this evening, so
Nice.
I was glad to catch the end of Victoria's presentation. I work at the School of Architecture in Wellington and have been on the executive committee of the Buildings and Community Systems IEA group for a number of years. It's probably enough from me. Thanks.
Thank you, Michael. And we'll go around. I think you know me. My name is Melis Tiliano. I work for Natural Resources Canada, and I'm the Energy in Buildings and Communities Chair for the time being. Louis, do you want to present yourself?
Yes, hello, I'm Louis Bourru from France. I'm working in the CEREMA state agency who is working on new building regulations in France.
Thank you. And Takao? Sorry.
Thank you, Mary. My name is Takao Sawachi, and previously I was working for Building Research Institute, which another Japanese participant, Shotaro Yagi, is working for. But Shotaro Yagi, he could not show himself because I guess he is working at the ministry. He has been working for the ministry for 1 year. I guess it will be finished by the end of May. But anyway, they are very hard worker, and he's still working in the office of the ministry. So I guess he could not show himself. But anyway, I have been in charge of developing Japanese building energy code, residential and non-residential, and I am very interested in overheating issues. And lastly, I mentioned the expertise of Shotaro Yagi. He's an expert in life cycle analysis. So I think he will have an opportunity to make his presentation maybe 2 or 3 times later in this meeting. Thank you.
Thank you, Takao. Vincenzo?
Hello, my name is Vincenzo Corrado. I'm a professor of building physics and building energy systems at the Politecnico di Torino, Italy. And the focus of my research activities is energy performance modeling. I both use simulation and also standardized methods, and I'm also more interested and active in legislation and codes.
Thank you. Roberto?
Oh, hi, Roberto Lamberts, Professor of Civil Engineering, Federal University of Santa Catarina, Laboratory for Energy Efficiency in Buildings, and helping the government on developing standards.
Thank you. Michael?
Good evening. So my name is Michael Dodds. I work for the Australian Capital Territory Government based in Canberra in Central Australia. I work here predominantly on buildings policy, but I'm also involved in the development of energy efficiency and condensation management provisions in the Australian Building Code for both community, public, commercial and residential buildings.
Thank you. Ryan?
Hello, Ryan Kolker, Executive Director for Energy Resilience and Innovation at the International Code Council. Work to coordinate our activities in that space, and you'll hear from me in a few minutes.
Thank you. Indeed. Victoria?
Hello, I'm Victoria Threadwell. I'm a senior building scientist at the Ministry of Business, Innovation and Employment. It is a mouthful. And I'm in the technical teams that's behind our building regulations. I was going to mention that we've got current projects on ventilation, internal moisture, as in surface and interstitial moisture, and also we're overhauling our energy efficiency requirements all in parallel with this piece of overheating work. So there's lots of opportunities for us to kind of learn about the interfaces of these different systems within buildings and to create something or to update the requirements or create new requirements where needed. So it's a really interesting piece of work to be leading from the overheating perspective, especially when the opportunity from the other code clauses perspectives to actually make a change, for example, ventilation requirements. Yeah.
Thank you, Victoria. And Richard.
Kia ora. Richard London. I'm Victoria's manager, manager for building performance at the ministry. We're government regulator, previous architect, building scientist, acoustic engineer, and my team has building services, plumbing, hydraulics, building scientists and architects, all working to cover 30 of our 38 technical building code clauses. So we cover a lot of territory. And this is just one of the topics, and as Victoria's alluded to, we look at these as buildings as a system.
Thank you, Richard. And we go to our second presentation. Ryan, are you ready to present your work on overheating?
Yes, hello, and appreciate the opportunity to share what's going on in the U.S. and around the International Code Council. I did want to sort of provide a little bit of context, because unlike many codes and standards organizations internationally, ICC is a nonprofit private sector organization that develops model building codes and a lot of the support mechanisms that make them work effectively. So certainly personnel training and certification, but we also do product evaluation and accreditation, providing software tools for jurisdictions, really looking at a very holistic approach to building regulatory processes. While based in the US, we do sort of take a global perspective and do work internationally, not necessarily specifically around codes and standards, but many of those support mechanisms that I mentioned. So just wanted to capture some of that, but also some of our codes are actually used internationally as well, and we've captured them here, particularly in the Middle East, Caribbean, and some in South America as well. So we take a sort of holistic approach through 15 model codes that cover many aspects of the built environment, which also provides opportunities to address sort of challenges through multiple different perspectives or multiple different avenues. And we'll talk about a few of those in a few minutes. I think one of the sort of important aspects of the sort of model code development process is that it is an open consensus-based process that drives what's ultimately included into the model codes. So ICC does not write the codes. We facilitate the process that writes the codes. So we engage stakeholders from across the entire built environment, basically come together on a 3-year cycle to determine what's included in the next edition of the codes. It's also important to note that because they are model codes, they are adopted at the state and local level with their own amendments on their own different timelines. And so the map here sort of captures where various different states are relative to the residential energy code provisions. And as you see, they're widely variable across the U.S. And so, while the map shows sort of equivalency, how the various different states reach that equivalency is different. And so, even neighboring states that are on the same edition of the code may have different requirements. It gets even more complicated because in some states, the code adoption process is left to local governments. And so you may have 2 jurisdictions that are right next to each other in the same state that have different code requirements. And so that really creates complexity in the codes process. I will note that we do have 16 different climate zones across the US as well. I'll share a little bit in a few minutes how that has changed recently. So we do have a residential energy code and a commercial code. Both have multiple different compliance options. I would say the primary paths that are used in both of those are prescriptive. So basically, this is what you need to do, and this is how you need to do it. We do have simulated building performance, and then for the compliance options on the residential side, we do have an energy rating index, which is a fairly recent addition. On the commercial side, again, prescriptive compliance, simulated performance requirements. We have ASHRAE standard 90.1 as an alternative compliance path as well. So some of the existing heat mitigation strategies that we have in the code, the energy code in particular is a very comprehensive approach, but mostly focused on efficiency rather than health or comfort, but certainly some considerations around mold and moisture. The code does not currently have minimum cooling requirements. And as I mentioned, largely prescriptive based with some performance pathways to demonstrate equivalency. Some of the focus areas we've seen around energy performance, a focus on insulation and the building envelope, solar heat gain requirements, window to wall ratios, ventilation and air change requirements, duct sealing, cool roofs and solar reflectance, and shading. And so those are sort of the predominant strategies that we see within the energy code. Relative to the 2027 development process, I mentioned those 15 codes. So we are currently in the final stages of the development process for the 2027 editions. We did establish an extreme heat working group in advance of the 2027 development process to develop proposals for inclusion in the International Building Code, International Mechanical Code, International Residential Code, and International Property Maintenance Code. So really identifying, several different pathways to include such requirements within the code. The Extreme Heat Working Group was looking to set cooling requirements. Right now, only heating requirements are covered within the code. And so, those cooling requirements would be based off of, active or passive measures around temperature and humidity. But ultimately, those proposals did not make it through the process and will be, sort of reconsidered or reevaluated for the 2030 editions of the codes. Relative to the 2027 International Energy Conservation Code, again, which is currently in development, they are considering new provisions around cool roofs, solar reflectance, and thermal emittance, tighter fenestration U values, and new options for permanent automated shading as part of compliance requirements. Some of the sort of prior activities within the international codes, in 2021, we did see a climate zone map update to reflect the changes in what we're seeing, relative to historic data around the climate zones. About 10% of counties, those in red here, were moved to lower or warmer climate zones. And so we've seen, that sort of movement sort of reflecting the changes that we've seen, in temperatures. And then also in 2021, we saw updates again on duct sealing and testing, air leakage, and cool roofs. I mentioned a lot of the activities occur at the state and local level. And so that's really an opportunity to sort of see best practices, see opportunities at the local level, which then could be incorporated into future editions of the model codes. So we have seen minimum cooling requirements, as you see here, largely in the Southwest, where we see a lot of hot and humid or hot sort of climates. Some activities as well in Chicago, which has notorious challenges with heat waves, and Washington, D.C. as well. But these are largely contained in rental housing or landlord laws, and not necessarily the building code requirements. We've also seen some activities, and I think Ellen may have presented on this previously, looking at opportunities through energy codes to enhance resilience, particularly the concept of passive survivability. So if there is a extreme weather event, the power goes out, and you have heat wave or cold snaps, the amount of time that folks can remain in their buildings comfortably or healthily certainly increases with the adoption of building codes, which is the middle purple there. Orange is existing building stock, and then the green is something like passive house. And so really sort of building out the case for increased focus on building codes as a resilience strategy, and maybe more holistic approach to addressing passive survivability and heat challenges in buildings. So that's what I have. I know Tristan recently joined, and MBI certainly works to sort of take the work that happens at the model code process and support incorporation at the state and local level. So I know he's going to share a couple projects that they have in this space as well. So thanks for the opportunity.
Thank you, Ryan. That was very broad and interesting presentation. Vincenzo.
Yeah, thank you very much for your very interesting presentation. You mentioned ventilation and air change, but my question is ventilation mainly considered for indoor air quality purposes, or do you also foster ventilative cooling in your codes?
It's mostly for health.
So for indoor air quality, not
indoor air quality,
cooling.
yes.
Yeah. Thank you.
Thank you.
Like the process is similar in Canada for the codes. We have it's not a non-profit. It's basically a government organization occupied by volunteers, and then the provinces essentially adopted through their own legislature with their own modifications. So it's very similar in that respect. Michael.
Hi, thanks for the presentation. Ryan, are there any jurisdictions, either at state or local level in the US, that require the use of a forward-looking climate file if they're for building simulation? I'm not sure if this is already included in ASHRAE 90.1. So it may be picked up for those states or territories that have ASHRAE 90.1, but I was wondering if, is there much use of future-looking climate files?
There is not.
Okay.
It's very much backward-looking. We've seen a few places not on the sort of energy side, but some things like sea level rise in South Florida, where they have started to incorporate future-focused risk, but not very prevalent at this point.
Yeah. Okay. And is there anything in ASHRAE 90.1 that points towards future climate?
Not at this point, no.
Yeah. Okay.
No, the sort of the closest that we've gotten is that update of recent update of climate zones, sort of recognizing sort of those changes, but yeah, nothing future focused at this point. Okay, thanks.
Michael?
Michael, unmute.
Yeah, you're muted.
Yes, I was trying. Sorry, it's another climate question. I'm amused by the fact that I think we have half the number of climate zones that a place as vast as the United States have, but we do cover almost Canada to Mexico in terms of latitude, so that's our excuse at the moment. The question is, as a country that is surrounded by water, the definitions that we're inheriting from the British overheating standards of the climate risk and the risk of overheating are due to the closeness of the rest of Europe and the continental effect of these large heat waves, as I understand them being called. Do you have any other definitions that we could look at that might be related to Hawaii or the coasts of the United States that differ from that continental effect? Because I'm not convinced that that definition of risk and the way of constructing weather files to look at the risk is necessarily suited to our type of climate. And I can't say that I am familiar with anything other than this vast publication that came out of Canada a couple of years ago on the topic.
Yeah, I don't know that I have direct insight, but as I mentioned, the sort of adoption process happens at the state and local level, so there could be sort of very specific amendments that address local contexts. Yeah, that would probably be my best bet.
Right. Yeah, it's the construction of specialized climate risk overheating climates that is of interest to me, not the what you do or how often things overheat. That seems a reasonably well based in terms of discomfort. But thank you.
Yeah, and I think Tristan's going to share a couple projects at the more local level that they've been working on. So that may give you some insight as well.
That's the perfect segue then. Tristan, you're.
Alrighty, can you hear me?
Yep.
Okay, great. Sorry I was late. I forgot to set my alarm, but fortunately woke up early. I logged onto my computer and saw this. Was like, oh shoot. Yeah, I'm glad I made it. Good to see you all. Let me. I just have to download a copy of this and then share real quick.
Just to let you know, sometimes I did it too. Like, it's not obvious. Like, you wake up at 7 and then you have a meeting an hour before, and so that's a problem.
Alrighty. Great. So yeah, my name is Tristan Grant. I'm the Director of Codes and Policy with the New Buildings Institute. The New Buildings Institute is a national nonprofit that works in the energy and climate space. My team, the Codes and Policy team, works primarily in three primary ways. We staff national model code consensus committees like the International Energy Conservation Code, both the residential and commercial consensus committees. We also staff ASHRAE 90.1, ASHRAE 90.2, and ASHRAE 189.1, and get involved on a few others. In addition to staffing and working or volunteering working at the national model codes, we provide direct support to state and local jurisdictions on the development of their energy codes, energy policies, climate policies, and then we conduct technical gap research that's needed to help move proposals, measures, guidelines forward at those other two venues. Over the past few years, we have been we've developed and are advancing this definition of building energy resilience. Energy or resilience is a broad topic. We work in the energy space, and so we've really been focusing on building energy resilience, which combines our experience and expertise in the energy space and the building space, and is a logical extension to resilience. So this definition is largely consistent with other definitions of resilience, the capacity to withstand, respond to, and recover from acute and chronic stressors. We then bring in the fact that these stressors are impacting the maintenance of energy critical functions within a building, and those include habitable thermal conditions, provision of lighting, fresh air, delivery of potable water, powering of medical, refrigeration, and communication devices. So this definition is similar to and consistent with characterizations of energy resilience from the US Department of Energy and many other organizations. Most of those definitions and characterizations focus on energy system level resilience and reliability. And we're bringing this down to the building level. And so the DOE, the US Department of Energy characterization of energy resilience touches on, it says there's two primary components, that there is passive survivability and grid interactive efficient building technologies. We bring in this third characterization, which is the intentional design and use of active systems, including distributed energy systems, for buildings to function independently of the grid. And so we see the development and expansion of distributed energy, solar storage, wind, sub building level portable solar generators, portable storage, as an integral component of resilience at the building level, with or without an active grid connection. There's been a fair bit of research, both and resource development in this space, both by New Buildings Institute, but also others. Ryan mentioned a few times, and I believe Ellen Franconi from Pacific Northwest National Laboratory has been involved in this group before. PNNL, NREL, I think, what was it? Yeah, Lawrence Berkeley National Lab in the US Department of Energy put out this landmark study a few years ago, Enhancing Resilience in Buildings, which looked at how different buildings built to different energy codes performed during a grid outage. That was the graph that Ryan had up previously. And what we saw is that incremental improvements in the energy code prolong habitability in all of the climate zones studied in the US, both in heating events and in cooling events for longer periods of time. And so what we did through a Department of Energy funded project that went through the past few years, it's currently sitting in limbo with the current federal administration. We looked to codify that last step, which was Passive House, which is currently a voluntary certification program. It's not written in mandatory regulatory language, but it does show meaningful improvements in the passive performance of residential buildings in extreme heat and extreme cold events. So the Connecticut Clean Energy Group led this project, the Connecticut Climate Resilient Energy Code. The code was specific for multifamily affordable housing. There were several technical, governmental, university, health organizations that were involved with the development of this. That project first looked to define what the scope of the code is, and the definition that I presented earlier came out of some of this work to define what are the building functionality and operational capabilities of a resilient energy code. This project kicked off in 2023. It went through several stakeholder advisory processes, market engagement. There was an affordable housing advisory group with both affordable housing residents, but also stakeholders like developers, owner operators. There was a technical advisory group. We came up with straw man concepts for the code, which started very broad, everything under the sun for resilience, stormwater management, wildfire, everything like that, and got narrowed down to the core concepts of energy resilience. And then a draft of this was released in March of last year. The code has three primary categories of measures. Going from right to left, we have improved envelope and improved passive performance, which is looking at better opaque assemblies, improved glazing that is climate appropriate, improved air leakage, tightening the building, controlling that with balanced energy recovery ventilation, and then thermal bridge mitigation. We then look at defining what critical loads in the building are and specifying emergency power to emergency power systems that serve those loads. We came up with a two-pathway structure that allows a building owner or developer to select critical loads and power critical loads in each dwelling unit or in one central common space in the building. In both instances, there's a space requirement that needs to be served that needs to be served with heating and cooling. We came up with 35 square feet per building occupant. If you're doing it at the dwelling unit level, that's counted as dwelling unit occupants, which is calculated as the number of bedrooms plus one. So if you have a standard one bedroom unit, the space that is served with heating and cooling, ventilation, and lighting would be a minimum of 70 square feet. And the thought was this could be a bedroom. You could provide a bedroom with heating, cooling, ventilation, and that space would be habitable within the larger dwelling unit. Or you can have a central common area in the building that has 35 square feet per building occupant for folks to gather, congregate if the power goes down and that space is warm, has lighting, has ventilation, and folks are able to go there. And then we identified some other resilience measures, urban heat island mitigation measures, and emergency management procedures, both for and operations manuals, both for building operators, but also for residents, so that folks understand, hey, how do behavioral interventions play into the ability of this building to meet the design intent, which is to operate for X amount of time during a coincident extreme weather and grid disruption event, and also to communicate to the building operators, hey, we're in low power mode or emergency power mode. These are the systems that are on. This is how the system should be operated to prolong the length of life of the emergency power system. Pacific Northwest National Laboratory supported the analysis of this code. We looked at, or they looked at and identified standard effective temperature as one of the metrics that we would use to evaluate the performance of the code during the simulated outage. We drew from a LEED pilot credit for passive survivability, which establishes upper and lower comfort thresholds, and during a simulated outage looks at the the cumulative set degree hours above or below those thresholds. So that analysis was done for this project. In a later research project, New Buildings Institute looked at simulating this code similarly during a grid outage, but also bringing in metrics related to grid reliability, electric grid reliability, because our thought is that we're optimizing for energy resilience at the building level, but a lot of the technologies that we're using for this are actually good for the grid. They reduce grid peak demand. They introduce the opportunity for demand flexibility through the use of specialized controls or the storage. They have that dispatchable flexibility. And we also looked at a few additional metrics related to thermal resilience and habitability. And what we found was that for this code in Connecticut, there was significant improvement across almost all of the metrics. We did, I should have gone into this before. Connecticut is a mixed cool climate. It's climate zone 5A, which is, might even be officially a cold climate, but even what's classified as a cold climate in the US still sees significant heat during the summer. And so there is opportunity for overheating, heat stress. We're also seeing, obviously, as many places are, more unpredictable weather, wider bands of weather, especially extreme weather. So even where a place may be heating dominated, you still have significant periods throughout the year where you have high temperatures and active cooling is needed. So we optimized the Connecticut code and the passive measures around the cold event, the extreme cold, the heating event, because that was expected to drive the design and the sizing of the emergency power system, because there's less sunlight, the temperature differentials between the outdoor temp and the indoor temp are higher, and so you need more storage for that. We're looking at 40, 50 degree temperature differentials, rather than on the cooling side, it's 15, 20 degrees, trying to cool down to 26 degrees Celsius, 76 Fahrenheit. If I don't know if I got my around there. And because we optimized for that extreme cold heating event, there was a negative impact on the extreme heat cooling side, because you pile on insulation and you optimize glazing for heat gain and things like that. So we later took those findings and modified this to be more appropriate for extreme heat areas, lower climate zones, hotter climate zones, and also came up with some frameworks for how you can evaluate and mitigate any adverse impacts in areas that experience both extreme heat and extreme cold. If you like, everyone always likes the graphs more. These are easier to interpret than the tables. The yellow is our base case. That's a code minimum building. The hatched line going across is our threshold for cumulative set degree hours. And you can see during the cold event, we were able to extend the habitable, what we defined as the habitable condition, staying below this set degree hour threshold beyond the 7-day event. And on the right side in the heat event, you can see it pulled that forward just a little bit. So we weren't too concerned about this because, it had an impact, but we're still at 6.4 days of safety. This looked at this data, the simulation looked at historical 30-year period and selected the worst 7-day cold and 7-day heat event. And I already talked about this a bit. We brought in the grid reliability metrics, and part of the point here is to look at value stacking and how we can pull together disparate financial streams to help. If we can demonstrate that this is good for the utilities, that this is helping alleviate stress, this is helping reduce grid load, we're hoping we may be able to get these types of requirements into utility spending programs and things like that, so that they can take credit for the benefits that this brings to their utility transmission distribution lines, and can justify the cost of supporting some of these building level measures as energy system level hardening measures. We did an analysis of the solar and storage system used to meet the after we did all that design, we looked at if we were powering during this period, lighting, ventilation, all of the other stuff, how long, how would we size the emergency power solar and storage system to meet those loads for a 24, 48, 72 hour period. A microgrid consultant went through several exercises and found out that in the Connecticut area, participating in utility load management and demand response programs and the value of the solar electricity generation, we could size for a minimum duration of 26 hours. That's the duration during that simulated extreme event, or a typical duration of 59 hours. And the system would be net present value about a break even. So you could install this system that with this configuration can have a minimum duration of 1 day, typical duration of over 2 days, for about life cycle break even cost. How this showed up in our code, we've iterated this some, and we took that sizing criteria that the microgrid consultant had, and we brought that in as prescriptive solar requirements and prescriptive storage requirements, watt hour per square foot, that you need to install to get that minimum duration. We establish, and then we also created a performance path, which provided simulation guidelines to redo this analysis during the to redo this analysis, and then based on the results of that analysis, size the emergency power system. And so someone asked earlier if anything references future weather files. We do nod to that here. We kick it to the authority having jurisdiction, which is the local, right, the local government, whoever is adopting and enforcing this. So we give recommendations for how you can use either historical weather files or future weather files to select that 7-day window that we're going to do the analysis within. In the simulation guidelines, we actually do recommend looking at both of those and kind of doing a sensitivity analysis to see how much they differ, because for the purposes of designing active systems, like designing the heating and cooling, we don't necessarily want to install, or we don't necessarily want to design the capacity of those and the operation of those to this extreme future weather condition, because it wouldn't be appropriate for the typical operating conditions of the building. But we do think that's an important sensitivity analysis to get kind of the boundaries of operational range that the systems may operate under. Some other stuff that we've been thinking about is, okay, if you're looking at a long-term future weather, 25 years, right? And the projected change in the next 15 to 20 years is not that severe and not that different from the historical extreme weather average. It may make sense to defer some equipment sizing and selection for that case to later, at like year 15 or year 20, when you would be doing equipment replacements, because that's when we would expect to see the more significantly the difference start to come in more significantly. And so this code, we've been looking at how to, this was developed for Connecticut. Connecticut's planning to incorporate it into local incentive programs around solar and storage and around their affordable housing financing and some things like that. we've been taking this and playing with the model to see, okay, what does it look like if we develop this for ASHRAE 189.1, which is for commercial buildings, but covers residential occupancy, commercial permitted buildings. In the U.S. under the I codes, a commercial building is a building over 4 stories and up. So a commercially permitted residential occupancy building could be a 4-story residential building, or a 5-story, it could be a high rise. We've also been looking at what would this framework look like to introduce to ASHRAE 90.2, to the IECC residential, to the IECC commercial as optional appendices, as alternative compliance pathways, things like that. I was just going to plug quickly, we don't have the results of this work out yet, but we have been leading the Resilient Southwest Building Code Collaborative, which is a partnership with the city of Tucson in Arizona and 12 other jurisdictions down in the Southwest in New Mexico and Arizona. And this group has been with several other stakeholder groups, local consultants, developing a multi-hazard framework and multi-hazard measures. So looking broadly at environmental and climatic risk, and what it looks like to create a code appendix and design guidelines and measures related to everything from extreme heat, water scarcity, air quality, dust storms, wildfire, grid disruption, and how we develop and package that in an adaptable code framework or regulatory framework, because just the Southwest spans 5 climate zones that go from mixed cool to very, very desert hot. And it's also a home rule environment, which means that the local cities and local jurisdictions adopt the code. So we need to create something that's adaptive to local priorities, local needs, local environmental context, but that has all of those resources kind of under one skin. And we should have a draft of the first draft of the multi-hazard appendix out in the next month or so. And then that project will be continuing on for a few more years. And then I put the resources in here so that folks can click through and have those available.
Thank you very much, Tristan. Glad that you woke up in time.
Yeah, me too.
Richard, you have a question?
Yeah, thank you, Tristan. Again, really interesting to see the approach and the proactive approach to be looking at grid resilience as an example. One of the questions that's been happening here in New Zealand is what sort of infrastructure do we need to invest in terms of its longevity when we start to look at renewables and the effect of renewables on grid capacity and operation or efficient operation of our hydro lakes, as an example. Anyway, slide 14, you were showing battery capacity in the hours matrix there. What assumptions were you using for the battery life when considering the MPV break-even?
Sorry,
If
I
you're-
was muted.
yeah.
I was muted. At 10 years, and this one had a payback at 8.2. Is that consistent with what you're looking at or how you're evaluating?
Yeah, just it's interesting. What we're finding is obviously battery technology is getting better, and there seems to be some really good advances with some of the sodium batteries as opposed to lithium ion and what we call salt batteries. The idea there in terms of some of the capacity of those, were you thinking of distributed batteries being used at each residential building, or maybe sort of a community, should we say, industrial sized battery to which they can draw power on as they need to?
Yeah, for the purposes of our analysis, we assumed a central battery, because we were looking at most of the affordable housing, that social housing, it's often called in other countries, in the US is owned and operated by a single entity, and then the residents are tenants of that. And so it seemed like the ownership and operational structure of the systems would most likely be central ownership in the context that we were looking at it. But that's not prescribed. You know, we're not prescribing that in the code. In theory, there's flexibility in that you could potentially meet this with batteries on individual end uses, like, oh, we've got an integrated heat pump plus battery, or you could meet this with thermal storage. If I think it would get more complicated. It's not written that way right now, but we certainly recognize that thermal storage is often cheaper on like a per energy unit basis, but it's a little bit more design intensive, a little bit more context specific.
Certainly, there's been some discussions around, should we say, shared energy, where you've got larger, high-rise type apartment buildings, which maybe are overheating, and getting to some point of taking their energy away, storing it, and then using it at a time potentially with lower residential type buildings, again requires a large conglomerate or corporate body type arrangement where there's actually common ownership for that to actually become effective. We don't have many situations like that here in New Zealand, but it is something that we've certainly considered internally. Thank you.
Yeah, thank you.
Excellent, thank you. Michael.
I have yes, it's kind of a follow-on question. I'm used to seeing these kinds of studies in academia. Am I reading it correctly that you're requiring the provision of PV and battery in all new buildings? Or am I misreading what you've been presenting?
That would be what's required. This is not currently adopted. So this is a model of how you could integrate these requirements for. It's specific to multifamily residential buildings. Already, our energy codes require our commercial energy code, which covers commercial residential buildings, like I mentioned, has a minimum on-site solar requirement. So that's not new. That's not necessarily a new concept. It's actually very controversial in the code space whether that is appropriate or not. California has mandatory. I mean, California is like the 7th largest economy in the world. So they, as a state, have mandatory solar and mandatory storage requirements for some buildings. So they are going that direction. We're seeing a lot of jurisdictions, the jurisdictions that are moving quickly towards zero energy, zero carbon policies and codes are looking at the role of storage as an essential tool to reduce emissions over the next 20 years, even if utilities aren't sending emission signals now. They anticipate they will be at some point over the next, decade. But the way this is written right now, it's saying, yes, there's a minimum amount of on-site solar, and then the storage requirement is sized off of that microgrid analysis. When we've written, and there was the Connecticut project, we've made an adapted model of this and are developing that for ASHRAE 90.2 and 189.1. And in those frameworks for the national model codes, we are fuel agnostic. And we say, here's the storage capacity sizing and power sizing, but we're not actually saying it needs to be electric storage. We actually don't call it storage. We say the emergency power system sizing. So in theory, that could be a gas system. And from a climate perspective, maybe that's not great. from a resilience and life safety perspective, that's
Of course.
that is as resilient and good for the building occupants as an electric energy storage system. So, the way that these types of things are picked up often in the US is it'll get picked up by an incentive program where the state is giving some money to help build market capacity, labor force, get cost compression in a key industry. And they say, hey, comply with this and we'll give you $10,000 a dwelling unit or whatever. Similarly, this might be Connecticut was looking at, they have a solar and storage financing product through their green bank, I think. And so they were looking at referencing something like this in their solar and storage financing program. Like, hey, if you install that system in a building that meets these criteria, you qualify for this incentive. So it's likely not going to be mandatory minimum requirements for all buildings in the short term. I think longer term, we may see it required for certain like key sensitive populations, like you have assisted living facilities, places where it's hard for residents to relocate, serving vulnerable populations, old folks, young children, things like that. I could see it being more appropriate. So my guess is we'll see some sort of incremental, if and where it gets picked up, it'll be picked up in a more focused application.
Thank you, Tristan. Michael?
So 2 questions. So just leading on from what you were just saying about where it might be picked up, is there conversation about designating certain buildings, certain public community buildings to have this level of storage so that in a catastrophe there is somewhere for people to go that will have power? And yeah, is there any thinking layered on top of that to say that there must be a certain size of building per head of population or anything along those lines?
Thinking, yes, not in our current framework.
Yeah.
We at ASHRAE 189.1, which is the green building high performance standard for commercial buildings, from ASHRAE, it forms the basis of the International Green Construction Code for commercial buildings. They have a resilience task group. We've been working with that resilience task group to take these concepts from the Connecticut Code and adapt it to that. And that's been one of the central, I don't want to call it sticking points, but one of the central things is that, hey, this is really appropriate for other building types. And I think, that's the resilience hub concept, right? That you have a public building, a municipal building, a library, a stadium, a school, whatever. I think, and we've been thinking about this, I think it's a really important and logical next step. Establishing the boundaries are a lot harder, because all of the different buildings that you might select are different, right? Like a fire station versus a library versus a school all look very different in their typical operation. And then you also need to define what the emergency operation looks like. How many people are you expecting to congregate there? How long are they going to be there? What's the expectation of level of services from this facility? And all of that gets into operational design parameters that is more, I mean, it's local specific, it's context specific. Different people have different opinions about what that level of service and operational priorities should be. So I feel like that's something that we're hoping to get to that level of templated solution for other building types, or at least some operational characteristics, like you said, here's the minimum storage, or here's, regardless of what building type, here's what you should expect it to be able to do to be a resilience hub. But we don't have that yet.
Okay, so the second question was around passive survivability that you mentioned, and it was the fenestration and I guess the building performance, the envelope and fabric. Was that based on existing requirements within the Connecticut Building Code, or is that was enhanced, like a higher level of airtightness and I guess building performance that was used to? Because if I was reading one of the graphs properly, you were getting sort of 6 or 7 days worth of stable temperature before the building gave out.
Yeah, it was enhanced. And so let me. The yellow line is the existing code, and the green line is the advanced code. And so we layered on better U values for walls and roof, better U values for windows, tighter buildings, reduced thermal bridges, all that stuff, which helped in the cold event, hurt a little bit in the heat event. But again, the measures were optimized for that cold event. When we have in the 189 and 90.2 frameworks that we've developed, the passive extreme heat measures include glazing orientation requirements, like how much glazing you can have based on building orientation, maximum window to wall ratios. That we also introduced some mandatory active systems like ventilation bypass economizers, so that when the temperature is cooler outside than it is inside, it bypasses the heat exchange core and just brings in direct outdoor air for that free cooling. Low power air circulation, like ceiling fans, things that can move air and lower the sensible temperature, whatever the right way to refer to that is.
Yep.
And yeah.
So this is with battery backup. So this is
without
battery. So this is no power at all, or is
This is no power at all. And the line that we're crossing there is the cumulative set degree hours. That, like, if we're doing base 80 degrees Fahrenheit, 1 hour at 100 degrees could be 20 set degree hours, or 20 hours at 81 degrees would be 20 set degree hours. So this doesn't necessarily pick up the severity of risk associated with that temperature exceedance. And so this isn't the simulated full grid outage is not delivering ventilation, lighting, refrigeration, any of that stuff. And so when we went to sizing it, we would say, okay, what is it actually? We would set a thermal limit, and we would say, what does it actually use for heating, cooling, ventilation, lighting to operate it for that period? So the passive simulation is good for relative comparison of performance during that simulated outage, because we want to reduce the heating and cooling loads as much as possible. But then when we actually look to size the system, we look at the energy required for all of those connected loads that we specified during that 7-day simulated event. Or during the 2-day simulated, you can do it for whatever period you want.
Great, thank you.
Michael.
You're muted. Yeah, I did it
Trying
too.
to be polite and do that. Yes, sorry. You have this 216 hours for the underheating and overheating. Can you tell me where that comes from? I realize you said over 30 degrees Celsius or under 12 degrees Celsius, I think, is where you start counting these extreme degree hours. But why 216? It seems such a
rabbit out of the
precise
hat.
Right.
It is. So that was developed through a lead pilot credit. There's a lead pilot credit available for passive survivability, where if you do this and keep below 216 degree hours, you meet the lead pilot credit. That lead pilot credit, I've dug into the history a bit. There's not great records on that, but the Resilient Design Institute, Alex Wilson and folks over there, as well as some other stakeholders were involved in the development of that pilot credit. I don't know where that 216 degrees came from. We wanted to reference something so that it wasn't us just making it up for our study, but it does seem like like you said, that is a somewhat arbitrary threshold. Because of that, and because of what I mentioned earlier with like the severity of temperature exceedance building those set degree hours, we actually in our code language do put a maximum temperature exceedance. And when we size because we are sizing active systems, ultimately those active systems are going to keep it below this threshold. So that 216 is a helpful, I don't know, it's a helpful gauge when you're looking at comparative purposes, but it's not necessarily a scientific stay below this and you're safe, and go over that and you're dangerous.
You've created yet another academic rabbit hole to go down, which I'm sure I will at some point. But because I don't know how many of those kind of, why isn't it 200? It seems like a round number would be far more sensible in the end. But okay, thank you.
Richard.
It's another question for you there, Tristan. In terms of the way you did your heating and cooling, so you said during the cold period, power's out, don't have any power. Then it seemed to me that during the time when you had heating, you said what was the minimum amount of power that would be required. And I was just trying to think, you've got a power in terms of heat generation, but also you've got your plug loads. So how did you account for plug loads, or did you not? You just made an assumption that the power usage was going to be the plug load.
So when we went to size the system, we put the power back on in the model and isolated the load, like configured it to reflect the minimum critical load requirements. And we looked at the total energy needed over that time, both for the heating and the cooling event. So there was kind of two analyses. There was the passive performance with no power, and simulated that. And that was used to kind of calibrate the passive measures. And then there was the active performance during that same window with just the critical loads isolated. And that was used to come up with different sizing thresholds for the emergency power system.
Okay. So as an example, if you said you had a 100-watt bulb for lighting, you took into account firstly that you needed 100 watts of power, but you also took into account that that would be a heating source as well?
Yeah.
Okay.
So all of that showed up in the, I think, I didn't do the energy modeling, but I believe they used, Energy Plus or some other DOE2 simulation software, and that it picked up the dynamics of internal loads and heat gain and everything like that. Yeah.
Cool. Any other questions? Excellent. So we reached the end of our presentations for this session. I would like to thank very much the presenters, especially those, well, I think all of you either woke up early or stayed up late, so very much appreciated. We'll have another one of these meetings. I sent a little poll. If you haven't responded to it, please do. It will be a presentation from Sebastien from Canada, Takao, and Vincenzo next time.
Nice.
We all look forward to it.
Yes.
Thank you all for joining me, and talk to you in a few weeks.
Good evening.
Thank you.
Thank you.
Thank you.
Larry.
Take care.
Thank
Bye-bye.
you,
See
you all.
everybody.
Bye.
Bye.
See you all.
Bye.
Bye bye.
See
Bye.
you.